Okay, let's do some examples. Practice. Stats, math, all about practice, practice, practice. So our first example. According to credit monitoring firm TransUnion, the average customer debt. Okay, so it means, whoa, I'm thinking central limit theorem here, because central limit theorem tells me how averages are distributed. This is a stats class, so holy cow. Central limit theorem. Average customer debt for Albertans, consumer debt, for Albertans was $27,773. That's non-mortgage debt, by the way. We're going to assume that population standard deviation was 5,000. We're not exactly sure what it is. I'm just making that assumption. So the 27 grand-ish is accurate. The 5,000 is just my estimate. Right? It's worth what it's worth. Very little. So part A, what is the probability? In order to do any probability calculation, we do need to know what the probability distribution is. Okay. So when I start seeing, I see that word, it's bolded for a reason. I see the word probability, I'm thinking, okay, how is this thing distributed? I gotta have some I have to have a distribution, otherwise I can't do a probability. Okay, that in a random sample, sampling. When did I do sampling? Sampling distributions. That had something to do with central limit theorem. I'm not sure, but I read on in eager anticipation. That in a random sample of 36 accounts, the average, again, horns blaring, lights flashing, average, central limit theorem, right? Non-mortgage debt exceeds $28,000. Okay, so let's start off with what is our question. So we want to know what's the probability that the average, which we signify is X bar, exceeds, right? Exceeds is like greater than $28,000. So there's where we sit with the exceeds part. Okay, so now the next step is we have our parameters, right? Now, parameters exist outside the question. And by that means, this is our question. Probability that X bar is greater than 28,000. Our average is the 27,773 that we get from, I think this came from StatsCan, and our standard deviation of the 5,000. Okay. So we have a question and we have some data, and they do kind of start to get garbled up a little bit. And so it's important to note that if we never read A, mu and standard deviation is known to us, because without mu and standard deviation, A is meaningless. Okay. So now we know we're going to find a z-score. Okay. And our z-score is X. Now, because it's averages, it's going to be X bar minus the mean all over the standard deviation of X bar. Okay, because we're talking about averages here. It is the same XZ formula as we always have. Okay, it's nothing weird is going on here. It's not a special Z formula. It's the same Z formula, just based off of means rather than just straight X's. Now we know sigma X bar is equal to sigma over the square root of n, which is the 5,000 divided by the square root of 36. Okay. So we have all those elements. We can now bring them all together. So this 5,000 divided by the square root of 36 is 833.3333. Repeating 4 decimal places is plenty, okay? And so now we're going to find our z-score. Z is equal to, now, who's the X bar? Who is this? And oh my gosh, I got the X bar here, I got mu here. Where does the X bar come from? It comes from the question. We're asking about the question. It gives us sort of like, what's our cutoff point? Okay, 28,000 minus $27,773 all over $833. And I sorry, 833. It's not. It is actually, ironically enough, in dollars because standard deviation maintains the same units as means. That's why we like standard deviation over variance, because what the hell does dollars squared mean? I got no idea, right? Okay, so let's just draw a little picture before we get too far into that. Oh, by the way, this is going to equal to 0.27. I'm not going to round it to too many decimals because we're going to first look it up in tables and then we'll do it on Excel. Tables only go to 2 decimal spots anyway. Word of warning, this is a Z-score. Yeah, I know it looks a lot like a probability. Boy, wouldn't it be great if it were the probability? Yeah, it would be great. It would also be wrong. Okay, so that's just a Z-score. Even though, hey, it looks like a probability, it talks like a probability, it's not a probability. Okay, still one more step to go. Let's do let's just look at a quick picture here to see when I get an answer if it makes sense. Okay. Yes, I know. I've been drawing normal distributions for going on decades. You think I could draw one a little bit better? Yes, you think I could. Okay, so we have our mean, right? Got that from our Stats Canada data. And then we have our sliver of 28,000 here. And we want the probability that it's greater than 28,000, so that's that area over here, right? Now, we do know that 27,773 is in the middle, the mean and the median, because it's a symmetric distribution. Remember, normal distribution is a symmetric distribution. So we would expect half the observations to be to the right, half to the left of $27,773. Okay. So we know that if half is to the right of $27,773, then less than half must be to the right of 28,000. Right? That sort of makes intuitive sense. So that when we get an answer, we're expecting this answer to be less than a half. Right? We don't want to write something down that's we know is stupid, right? We don't want to be stupid. Business people, right? We gotta first of all, we gotta look real cool. Can't look stupid. Then we gotta be smart. So not only can you not look stupid, but then the second step is you gotta be smart. But the first step is always don't look stupid. So we've got that, and that's our action plan. Okay, so now we can roll over to the tables. And I got my tables, and these are tables drawn from the textbook and would have been what you would have used in Management Science 103. Okay, Stat 151. I think the Weiss textbook uses very similar kind of tables, if I remember correctly. Nevertheless, be very careful. You know, when you look at that wording on the left, it says provides area to the left of a given Z value. Okay? Not all tables automatically provide areas to the left. Some provide areas to the right, and so you just have to be aware of the situation that your tables are showing. Area to the left is not what we want, right? We want area to the right. Right? Area is on the right, this left. So now I have to make an adjustment, right? Now, I know that the area to the right of 28,000 plus the area to the left of 28,000 adds up to 1. This is no other place to go. So if I have the area to the left and I want the area to the right, I take the complement. I go 1 minus whatever it is that area is to the left, which is what our tables give us. So, long story short, is the probability that X bar is greater than 28,000 is equal to 1 minus the probability that X bar is less than 28,000. Now you're starting to say, ooh, hey, what about equals to 28,000? Hey, Wesley, come on. It's like our second video clip. What the hell is with the equal sign? What's going on here, man? Losing confidence. The probability of any exact point with a continuous distribution is 0. So we leave it in there, we don't leave it in there, whatever. Okay, and that's because we're not talking about 28,000. We're talking about 28,000 in an infinite string of zeros, not 28,000.0000001. No, that's greater than 28,000. Right? We're talking about 28,000.0000000 forever. Right? Now, when you look at all the number of choices of real numbers, there's an infinite choice. You pick in one of the infinite choices, the limit of that becomes about 0. You could also do with integral calculus and find the area under a single point is also 0. What's really cool is if you add up those zeros enough, they add up to 1. This math is a crazy thing, isn't it? Okay, so we have that. Now this, we can get this guy right out of the tables there. Or from Excel, whichever you prefer. We'll do both. Okay. So now I'm looking in my tables for 0.27. Set is 0.27, so 0.6064. However, that is less than 28,000, right? Area to the left. So mine is 0.06064, and then that equals to, I gotta punch it into the calculator. And what do we get? 0.3936. There we go. Easy peasy, right? So now let's look at this thing from the perspective of Excel. So let's pull our Excel into our window. Okay. So now, when we start to think of Norm is our friend. Who is this Norm person? What's Norm? Who's Norm? Okay, well, Norm is going to be what we use in order to find our normal probability. Okay, so if I go equals to norm, and we have a whole bunch of choices. Norm.dist, norm.inv, norm.s.dist, norm.s.inv, norm.dist, norm.inv, norm's.dist, norm's.inv. Holy cow. Hey, well, the first four are the modern Excel way of doing what the last four or the second four did, except with more dots and longer commands. So somehow in the realm of Redmond, Washington, and in the bowels of the Microsoft campus, it makes sense that we simplify things by making them more complicated. Go figure, right? Okay, so let's go with the norm.dist. Dist, go with the modern way. And it says returns the normal distribution for the specified mean and standard deviation. Oh, cool, right? Open that bracket up. And then I see, hey, hinting, x, mean, standard deviation, cumulative. Okay, so I'm just gonna make the screen a little bit bigger here so we can kind of see what these things are. X, that is just the 28,000, right? We're just doing it the same way as we did it when we were looking it up in the tables. Okay, the mean is the 2773, making sure I got all those sevens in there. Standard deviation, 0.333. Cumulative. Now, there is very little reason why we would do the PDF on this. It doesn't give us a probability of an exact point or anything like that. It just leads to heartbreak. Now, we notice that the formula is 0.6073. And that is because when we rounded to 0.27, we rounded, right? And that rounding cost us a little bit. Excel doesn't do the rounding. It takes us to a lot more decimal spots. So slightly different answer. Not a catastrophe either way. They're both pretty close. But just like we had before, we still have to do one more step, right? We still are finding the complement. So Excel still gives us only the area to the left, just like the table does. Okay, so we get 0.392657. The tables gave us 0.3936. It again, rounding, because the tables only go to 2 decimal spots, we sacrifice a little bit there. That's just the way it goes. But what can you do, right? Okay, and that seals up that one. Let's look at something a little bit more challenging now, right? What is the probability that in a random sample of 49 accounts, the average debt is between a couple of numbers? Okay, this is a little more exciting. Now, We still have the same mean as we had before, right? Because we're still talking about the same population of interest. So that's all the same. Okay. It's now a random sample of 49, so n is 49. So when we think of sigma x bar, we're thinking 5,000 divided by the square root of 49. So slightly different value. Okay, but nothing we can't handle. Okay. I'm just going to leave that as is for now. And now we want the average debt is between two numbers. Okay, we live in a world that we only have the answers to the left. Okay. So we think of our diagram, what's going to happen? Well, I have my mean in the middle, 27,773. Everything looks the same, eh? And then not to scale, just so I can just draw stuff out here. So it's not to scale. I have on the high end the 28,500, and I have on the low end the 27,000. Again, not to scale. It's only so I can draw stuff up here. Okay, and we're interested in the middle. When I use Excel, when I use the tables, I get to the left end. So if I was to find the probability that x bar is to the left of 28,500, that would get me from 28,000 all the way down to the edges of the universe. Okay. It means there's some spot, there's some info, there's some area I don't care about, right? Specifically that area to the left of 27,000. Okay. So I'm going to subtract off the area I'm not interested in. All right. Which one of these areas doesn't belong here? Which one of them do we want to get rid of? No. I'm doing Sesame Street no justice there. Okay. So when I take away those two, I'm left with the juicy center in the middle of the donut, which is what I want. Okay. All right. I find the probability that x bar is less than 28,500, subtract from it that area that we're not interested in, that's out of our zone of interest. Remember, we only care of the area between 27,000 and 28,500. If it's beyond 27, if it's less than 27,000, we don't care about it. It's dead to us. Get rid of it. Hack it out. Subtract it. Right? Okay, so less than equal to 27,000. So step 1 and step 2. And then we subtract to get the difference, and that's our win. Which means there are two Z-scores. Yeah, wouldn't it be great if you could just do blah, 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 do it as one Z-score? Yes, would be great. Again, would be wrong. So we have two calculations going on here, and then we subtract them. Two probability calculations that we essentially do individually, and then at the very end we subtract the two probabilities. And this goes whether we're doing it by hand or with the tables or we're doing it on Excel. Doesn't matter. Okay. So our first step is we'll find that probability that x bar is less than 28,500. Right? It's like its own little question, its own little Z-score, and so on. Right? Z equals to 28,500 minus the mean, all over that standard deviation of 5,000 divided by square root 49, which I would do in brackets. Sometimes order of operations can be a little funky, okay? And when I do that, I get a Z-score of 1.0178. Right, so essentially now I'm finding the probability that Z is less than, right, less than. Z is just a transformation, right? The problem, the initial, the normal distribution still exists. Everything still exists. It's just a transformation of one normal probability distribution into the standard normal. Z is less than 1.0178, and then I can look this up in the tables, right? And let's flip to the table, and I look for 1.01, 1.0. Ooh, So we do what? 1.02? Yeah, it's rounded a little bit. Again, when we do it on Excel, we're going to get a little bit more precision because we won't be facing this rounding issue. But I see that I get 0.08461. That is the probability that X bar is less than 28,500. Now, concurrently to that, let's look at step number 2. Probability that X bar is less than 27,000. Right? So now that it's got its own little z-score, 27,000 minus, same mean though, can be a negative number, not a problem. Okay. And when we punch that in, we get a z-score of minus 1.0822. Okay. Now, a couple things to keep in mind. Yes, I know we don't. There are negative values on z-score tables, but that's kind of boring. 822. Okay, so what's the transformation? Probability that z is less than 1.0822. We'll do this on Excel. We'll see that this is very easy to deal with. I'll just do it by hand, just only because it's very illustrative, because it gives us a sense for how that normal distribution kind of works and how it spins in that universe. Recognize the normal distribution is symmetric, right? So when I think of probability that z, right, is less than a negative value, right? This is the standard normal now. This is standard normal. It's out here, right? And that's just our minus 1.0822. That is the same as this area here to the right of positive 1.822, right? These two areas are the same. Right? So we can look at it in probability that x, z is greater than 1.0822. When we do that, now it becomes the same as the problem we just did a couple of seconds ago, right? Where we are trying to find the probability that x bar is greater than 28,000. Right? Means we're going to be taking a complement. So this will be equal to 1 minus the probability that z is less than positive 1.822. Okay? So there's a lot of nuance in that particular question, right? There's the whole idea of symmetry, which means we're just flipping it over so that we have positive values. That's the sort of the first thing that we do. Our tables, okay, only provide us with the area to the left. So now we got to think, well, I don't want the area to the left anymore because I flipped it over, right? Whereas before I wanted area to the left because it was to the left of the negative number. Now that I flip it over, the pancake, I want the area to the right of that number, which is 1 minus the z is less than a positive 1.0822. Okay. And so now I look at 1.08, 1.08, and we get what, about 0.8599. So 1 minus 0.8599, and that breaks down to 0.1401. Okay, so now we have the two probabilities. Okay, and so to finish this whole big saga, the probability that x bar is less than 28,500 but greater than 27,000, is equal to 0.8461, which is the probability that it's less than 28,500, minus the area we are uninterested in, right? The area to the left of 27,000, and that equals to 0.706. So multi-steps to that particular process. Now let's quickly kind of zoom over it in Excel, recognizing that of course our friends in the lab will do this on Excel for us in addition. Okay, so let's just freeze that. Go back to the question. Just move Excel over here a little bit so we're working with it in the same screen. Okay. So we have our probability of our X bar is less than 28,500. Okay. So again, we're back to our good friend Norm. Norm dot dist. And the kids, the lab instructors, they just happen to be former students, and anybody under 56 years old is a kid to me. And so they'll show you how to set it up nicely. This is a little bit more calculator oriented. If you wanted to make it very pretty, you would have the X here, you'd have the standard deviation in a separate cell, you'd have the mu, the mean, in a separate cell, and so on. Okay, so I'm a little bit shortcutting this a little bit, but the lab instructors will give you a little bit better guidance on how to make it look a lot nicer than I am. Okay, now I'm just going to roll through this because we've already done this once before. 27, and I see all the arguments, mean, and then my standard deviation. And obviously it's cumulative, right? Because we don't care about it anywhere else. Now let's look at the shortcut. I could bring a formula in there, no big deal. That's the beauty of Excel. Yes, we have that there, right? And that's pretty close to what we had. We had 0.8461, 0.8456. Again, the rounding issue is what's doing it for us. Norm.dist again, and this time the 27,000, and we'll see that in this case this will really be labor saving because this will cut down a lot of our efforts, right? Because we don't have to do near as much stress stuff, right? And see 0.139582. Very close to what we had before, but man, was this ever easier, right? And then the last one just equals to the subtraction of the two probabilities. Right. So very close. I mean, it was 706. We got 706, 0.032, a couple little extra decimal spots. But the tables were fairly accurate in this regard. But you can kind of see that once you get a familiarity with Excel we could really do these calculations very, very quickly. It's very nice. Okay, on with some more of the show. According to Stats Canada, the average daily vehicular commute time in Edmonton, 46 minutes. That's there and back. Assuming commute time follows an exponential distribution, which is not unreasonable. A lot of things that are related to time follow an exponential distribution. Time until some event is often modeled at exponential distribution. When you take Management Science 352 and you do, the beloved waiting lines chapter, time until the next call or time until the next service is provided follows an exponential distribution. If you're curious, the time until the motherboard on your computer fails typically follows an exponential distribution, as is the time until Your Apple iPhone dies, follows some exponential distribution as well. So exponential we see a lot in the realm of time. Okay. Now let's survey some amount of consumers. So mu is 46. Standard deviation is what? And you're going, what? What? Standard deviation is not in there. What the heck? Now, if you came from Stat 151 and you go, what the heck? Legitimate beef, because you didn't take this. You didn't do exponential distributions. You're coming out of 103. You're saying, hey, I am all over this. I remember exponential distributions from Management Science 103. Right? Tick, tick, tick. One of the wonderful properties of the exponential distribution is the mean and the standard deviation are the same. There's only one parameter in the exponential distribution. That is the mean. So standard deviation, 46. Now it follows an exponential distribution. Oh boy. Let's say we survey some amount of customers. Normally I would ask you this in person, but let's go with, let's say 36. Huh? 36? No. So I'm just picking stuff that works nice in your head. So, square roots of 36 is 6. Yeah. Age of calculators really doesn't matter. Let's find the probability commute time is less than some amount. Let's say probability. The average commute time, X bar, is less than, I don't know. Let's go with 40 minutes here. Yeah. Average. Now, even though the original distribution is exponential, we don't care about that because we're talking averages here, and averages are normally distributed. All right. So the fact that it came from an exponential distribution doesn't matter. The fact that you don't remember anything about the exponential distribution, it doesn't much matter. The fact that I know you didn't take it in Stat 151 if you took Stat 151, don't worry. Doesn't matter. So now we have X bar less than 40. Okay, awesome. Sample size of 36. So the sample standard deviation of those means is that 46 divided by the square root of 36. Right? We'll find our z-score like we always do. Right? X bar, 40. Remember our z-score formula? X bar minus mu over sigma X bar. So 40 minus the 46. Ooh, negative number. And then 46 divided by the square root of 36. We find our z-score. Usual way. You can then look it up in the tables, or we can use Excel to solve it for us. Whichever way we prefer, right? We've got a lot of flexibility in all this. So when we find the z-score, we get minus 0.7826, let's go with. Okay. Now you may be asking yourself, why all these z-scores that look like probabilities? And that's a little bit deliberative. Only because I really want to emphasize that a z-score is not a probability. And in the past, that's been something that gets a little bit confused in that if folks see a z-score that's between 0 and 1 or as a decimal number, that somehow, hey, that looks like a probability. Maybe they start to second guess themselves and start to think, well, maybe that's the probability. I just don't want that to happen. So the ones where z is 2.2 is easy. These are ones that are meant to be a little bit more sinister, so that we practice and we get used to the sinister aspect of it, and then it doesn't bother us if we see it in a pressure situation. Okay. So we want the probability that z less than negative, 0.7826. And we understand with this, like we did before with the symmetry of the tables, that is the same as 1 minus the probability that z is greater than, that is the same as z is greater than point. I'll just not jump too many steps at once. right? Which then is equal to 1 minus the probability that Z is less than the 0.7826. Okay. This is lookupable in the tables. I mean, only to 2 decimal spots. I mean, that is sort of the sacrifice that we make, but it's still workable. We get 1 minus, and let's go look that up in the tables right now. Okay, 0.78, and we get 0.7823. Oh man, that is I didn't forgot about that. that is a little more sinister than what one would have wanted to make it. Actually, I forget about some of these examples until I review them and go, oh, that's nasty, that's mean, because they're so close to each other. But anyway, probability 0.2177. Okay, let's pull in our good friend Excel here. Right, and pull in Excel into our screen, and again, same as what we had before, except now we don't have to worry about anything too terribly tricky. Right, we still have our friend norm, right? Dot dist. Oops. And we still have our x, which we formulated the problem, so we know what x is. We know it's 40. We know that the mean is 46. Yeah. We know that the standard deviation is 46 divided by the square root of 36, or we could have figured it out. And we're always interested in cumulative distribution, because the probability density function doesn't make any sense to us. Now this gives us straight to the less than or equal to, right? So the only thing that made this complicated by doing the tables is the fact that we had positive tables, which, you know, this is an open book exam, or if this is an open book exam, you know, you have whatever tables you like, and you'd have the negative side of the tables, or you could use Excel, and Excel gives you the quick answer. So with tables, we got 0.2177. With Excel, we got 0.21693. The Excel answer is a little bit more precise answer because the tables did have some rounding attached to it. Okay. This one here, I'm gonna set it up and just leave the grunt calculations to you. If the sample size were 49, okay, so n is equal to 49. What would the probability? Okay, then you would do that, whatever. Okay. Now, what's really interesting is find the probability of a difference in excess of 2 minutes. Okay. So that is pretty cool, because now we have to sort of think it through a little bit. So when you see the diagram on that one, now we're talking about averages, so the fact that the exponential distribution is pretty right skewed, not really hurting us here, because we're only dealing with the averages. Average is still 46 minutes. In excess of differences in excess of 2 minutes of that, which means he's got 48 here. So we want that area. And then 2 minutes less than 46 is 44. And the area to the left of 44. So we want the probability that x bar is greater than 48. And then we add to that, that's a little bit different, the probability that x bar is less than 44. Now we want to be very careful that we don't add, we want to make sure, okay, so that area is out there, and that looks all fine, right? Right? Not going to add up, not going to be greater than 1. There's no overlapping. That's our big sin, right? Is if there's some overlapping and then we get a probability greater than 1, that's a world of hurt. That's like dividing by 0. The world ends at that point. So we have that. Now you could see that, hey, I could have found the middle gooey part, got 1 minus that, just like we found the middle gooey parts before, right? Now it's a pretty straightforward process. This one, just a slightly different way of looking at what's essentially the same problem. Okay, so I leave that up to you to do that calculation and come up with those answers. But that's essentially how we would start the process off. After that, we've got all the basic tools in order to make this work. Okay. Couple of questions, and then we'll wrap this up. Is the life expectancy of a particular brand of hairdryer has a mean? All right, we know how means are distributed, right? They follow normal distribution. Mean of 50 months, population standard deviation of 8 months. Okay. What is the probability that a random sample of 16 hairdryers will have an average working lifetime of more than 52 hours? Don't know. How do I not? What do you mean you don't know? What kind of answer is don't know? I have no idea what distribution this follows. Right? N is less than 30. I don't have a big enough sample size to say central limit theorem here. I don't. I need 30 or more. I got 16 with an unknown distribution. Can't do it. Really don't know. So, there you go. Don't know. Sample size less than 30. Can't use central limit theorem. End of story. Nasty, tricky, eh? Sinister. Oh. But at this point, I get the question is, would all the exam questions be like this? No. Every kind of trick, every kind of twist that you would have possibly ever encountered in your first stats class, I've pretty much kind of thrown this into 1 week's worth of lectures. Okay, so it's a highly concentrated sense of nuance and all the things that could possibly trip you up. Next thing, what is the probability that a random sample of 64 hairdryers will have an average working lifetime of more than 52 months? That we can do, right? And greater than 30, central limit theorem. We're great, okay? That one we can do. Non-controversial, not a big deal. Using tables, you're looking at an answer of about 0.3745, and using Excel, you'll get pretty close to that as well. Do that one on your own. Keep doing it until you get about 0.3745. Okay. And the very last one, 95% of this brand of hairdryer will have an average life expectancy of at least how many months? Using the information from part B. Okay, so we have N is 64. Mu we still have from the beginning here of 50. Sigma was 8. Sigma X bar, in this particular case, is 8 over the square root is 64. Yeah, that's not very random choices. Okay, so it's 1, just to kind of make some of the math a little easier to work with us, because there's a little complication to this particular question. Now, this question is not asking for a probability. Right? It's a little bit of a twist here, kind of like the climax to this wonderful story here. There's the plot twist. What happens if you're given a probability, and now you need to find the X associated with that probability? Holy cow, right? Fascinating. This one's, I like to draw a picture. Okay. All right, 95% of brands of hair industry will have an average lifespan of at least how many months? At least. Sounds like greater than or equal to, right? At least that amount or more. Suggests that this X is out here. And the probability to the right of that X must be the 0.95. 95% of them are greater than this value of X. All I know is because the mean is 50, that this value of X is less than 50 months. Well, that I'm pretty sure of. I'm also pretty sure that the area to the right, or to the left of X, is 0.05, right? Because the area to the right plus the area to the left, they add up to 1. If the area to the right is 0.95, the area to the left must be 0.05. Okay, so I have these pieces of information. So, because I know my tables and my Excel are all less thans, I'm more interested in the less than probability than the greater than probability. So probability, oops, I should have put a little bar on that X bar. Oh, my bad. Probability X bar is less than some value. little x. Ooh, tricky. Capital X means random variable. Follows a distribution. All that kind of good stuff. Little x means there's a particular value. And little x represents a particular value. We just don't know what that particular value is. Anyway, the probability is 0.05. I still have a z-score. And z-score is still the go-to here. So what does that z equal to? Well, it equals to this x, which I really don't know what it is, minus the mean of 50 all over that standard deviation of 1. Okay, now, I'm getting closer, but I got one formula. I've got two unknowns in here, and I don't like that. So, let's go and figure out, using our tables, find that z. Once I find the z, the x is easy, right? So, we had the case where the z equal to x minus 50 all divided by 1. If we can't use Excel, then we have to find the z and then do the simple math. With Excel, we actually have a very nice and easy way that we can do this calculation. And it involves another norm. And this happens to be norm inv. Norm and dot inv. Now, norm, we see it says returns the inverse of the cumulative distribution for the specified mean and standard deviation. What that essentially means is we're going backwards. Up to this point, what we've done is we've had an x, we find a probability related to that x, whether it's a greater than or less than, whatever, it was a probability. Now we have the probability, and we're going to go backwards and find the x associated with that probability. Okay. So we need to know what that probability is, which we figured out, 0.05. We still have a mean of 50, and we still have the standard deviation, which is 1. Okay? And then, boom, answer, x is equal to 48.3551 months, right? Nice and easy. Now, what if you didn't have Excel? What does that look like? That looks like it's not near as easy, okay? So now you have to find the z. So we're thinking, just to refresh, we have a z. We need to know what this minus this z value is, which we know is to be negative, with the 0.05. Got the middle. Let's go minus z there, it's just 0, and a positive z of the same value, but this area is 0.05 as well. Okay. The area below the positive z is going to be 0.95. So we have a probability that the random variable z is less than this other little z here, is equal to 0.95. Okay? So that's a little bit of a nuanced, tricky transition that we didn't have to worry about when we did Excel. Right? The technology does help us. We still have to know how to set it up, but boy, this is a lot of finicky stuff because we have a table. Okay, so let's look at our tables here. And now I'm looking for 0.95. Now where's the 0.9? It's a probability. Where do the probabilities live? In the middle gooey part of this table. Right, middle gooey part. And I'm looking for probabilities. Now I happen to know where it's going to end up because this is a very popular z-score. And it ends up 0.945, 0.9505. Right? And, you don't have to you could pick 1.64, 1.65. You can go with 1.645. Right? If you're a typical Canadian and you're just kind of going right up the middle here, it's not too much this way, it's not too much that way, let's go with 1.645. Okay. So we have that. Now, in our heads, however, we have to remember that this z-score over here is a negative value. Okay? And that becomes important when we start to do the calculation. So bringing it all together now, we're going to have minus 1.645. Why a minus? Because we're on the left-hand side of the distribution where the negatives live. We found the positive z, right, on the right-hand side. Now we got to go flip over to back where we were before, onto the negative side of the z's. X minus 50 over 1. Now we just cross multiply, and we get a pretty close answer to 48.3551. Well, very close to that one. Very, very, very close. All right? But a lot more brain sweat in this one. Okay? So give that one a nuanced think. It really tests how well you can visualize the normal distribution. Okay, awesome. Thank you.